Algebra 2 Honor students, today is Unit 12, Day 2, and today we're talking about the really important topic of log properties. Log properties are really important in order for us to be able to eventually solve equations, do some applications with logs. So you're going to see properties are really important as we go throughout the unit, but we have to learn what they are first. In order to get a glimpse into what log properties are, I'm going to have you evaluate some logs, and then we're going to make some conclusions about kind of each row. So like number one, row or letters A through C kind of have a connection. I mean, they are all log base 2 examples. And then there's definitely a connection going on in number 2 and number 3 as well. And maybe as you start filling in the exact values for each of these, you'll start realizing some of the connections that I want you to be making here. So what I want you to do is, as you're writing this down in your notes, when you write down log base 2 of 4, before you even go on to the next example, just write down what that equals. Remember, this is the exponent to which we raise this base to get the number on the inside here. So if you can fill these in pretty quickly as you go down the line here, I'm going to encourage you to hit pause, go ahead and fill just this piece in first. Once you have that piece filled in, then we're going to see what the connection looks like to log properties. If you're done hitting unpause, then what I'll have you go through is, what are the answers here? What are the exact values for each of these log expressions? Well, log base 2 of 4 is 2 because 2 squared is 4. Log base 2 of 8 is 3 because 2 cubed is 8. And finally, log base 2 of 32, maybe we just have to think a little bit harder about this one, but the answer there is 5. Okay, so again, I want you to start thinking about these expressions in log form and what the answers are, and if there's any kind of connections we can make here. Log base 3 of 3 is 1. Log base 3 of 9 is 2, right? 3 to the first is 3, 3 to the second is 9, 3 to the third is 27. So log base 3 of 27 is 3. And then last but not least, log base 5 in the last row here. Log base 5 of 1/5 is -1. Because 5 to the negative first would produce that fraction 1/5. Log base 5 of 125 is 3. And then log base 5 of 25 is 2. All right, so now that we have all 3 rows filled in, is there a connection between the values inside the logs and what these answers are? And can we sort of make some conclusions about what the log properties are going to be? Okay. Well, maybe something you've noticed is, I'm actually going to separate that last column C for a second. And if you look at the numbers 2 and 3, and I see that the number 5 is over here. Here are the numbers 1 and 2. This number over here is a 3. -1 and 3, this number is a 2. Maybe we're seeing the connection that, oh, okay, if I take the answers, 2 and 3, those add up to 5. And 1 and 2, and those add up to 3. So there's some sort of connection between these two and the sum of those answers equaling the value on the other side. Well, now I want you to take a look at what's going on inside the log. So look at those numbers 4 and 8. Here's 4, here's 8, here's 32. Here's 3, here's 9, here's 27. So we know what the connection is with the numbers on the outside. What about the numbers on the inside? What would I do with these 2 numbers to get to that number? What would I do with those numbers to get to this one? And then if you know the pattern already up there, you can apply it to the last rule. Are we thinking maybe do some multiplication, right? 4 times 8 is 32. That works. 3 times 9, 27. 1/5 times 125. Yeah, that will be 25 in the end. So that leads us into some log properties here. So there are going to be 3 of them that we list. The first one being, in general, the product rule. Okay, so if you have log base b of the product x times y, that can be written as log base b of the sum x plus log base b of y. So you can always take a product of 2 numbers on the inside here and expand that to a sum. Because look at what happened if I kind of work through this from the right side over to the left side. 32, if I break that up into 4 times 8, that's the same thing as log base 2 of 4 plus log base 2 of 8, because 2 plus 3 is 5. Okay, so that's the product that's really being illustrated in each of these examples up here. Okay, when you have log of a product, it expands to the addition of those 2 quantities. And I don't think it will be too much of a surprise if I said there's a quotient rule as well, log base b of x divided by y. You could actually even think of this as product if you bring the y to the numerator and make it x times y to the negative first. So you might get a little fancy there. But otherwise, we're not going to do that too often. We're just going to write it as log of the difference here. Log base b of x minus log base b of y. All right, so if we have those first two rules, the last rule that we're going to talk about is really important. When we go to solve equations later on, it's log base b of x to the y power. And the rule here is if you have a power that's going on here, you can bring that power out in front of the log. And I'm going to justify this last rule to you in just a moment. Because remember, raising something to a power is the same idea as repeated multiplication. So let me show you why this rule really works. And if we look at something like, log base b of 2 cubed, apparently that equals, bring the 3 out front, 3 log base b of 2. Well, the way I'm going to show you that is by writing 2 cubed as 2 times 2 times 2. And if we know that the first rule is true, because we saw it in 3 different cases up here. By the way, 3 cases doesn't justify that this rule always works. I'll tell you it does always work, but you kind of need a little bit of calculus to prove why it always works. So you'll have to wait a few years to get there. But we're going to trust that from those examples up at the top, this does always work. Well, log of a product is expanded to addition. So this could be written as log base b of 2 plus log base b of 2 plus log base b of 2 again. So if I expand multiplication to addition, I have 1, 2, I have 3 of those log base b of 2's, and hey, look at how those two things match. So in the end, could I just jump from this step to this step without the repeated multiplication? Yeah, I mean, we could bring the 3 out front and write it in this format. And sometimes I think a good way to think of this, if this is still a relevant reference point, it almost is like if you know the game Angry Birds, it almost looks like we're taking the value, that y up in the exponent, we're pulling it back and we're slingshotting it to the front. And I know that's probably a weird reference, especially if this is like the year like 2050 and I'm still teaching and nobody knows what Angry Birds is. But anyway, so we're going to bring down the y, slingshot it back, it's going to come to the front. That is the power rule. So we have 3 rules. We have a product rule, a quotient rule, and a power rule that are all very, very important within, like I said, later on, solving equations, some other types of applications with these properties. So the first thing we're going to do is practice expanding logs. And when I talk about expanding, what we're talking about is going from the form that we just had on the left side to the form that we have on the right side. Somehow I've lost my papers, but you'll get the idea. Okay. So here it is. I put it behind. Okay. So we're talking about going from this side to this side here. Expanding is working from left over to right. So if I gave you the example, log base 2 of x squared times y. There are 2 properties that we're going to use here. The 2 properties in question are the fact that we're multiplying these 2 things together, and we have a power. So the power rule means powers go to the front. Multiplication expands out to addition. So this is going to expand to 2 log base 2 of x, right? The 2 comes to the front of log base 2x. Then whenever you see multiplication, separate it to addition plus log base 2 of y. And that's it. That's as far as we can go with the expansion of the expression log base 2 of x squared times y. All right, moving on to something like, let's give you some quotients in here. Log base 3 of a cubed divided by b to the 4th. All right, this one, again, just uses 2 of our rules. We have a quotient. We also have some exponents that we're going to bring to the front. So the first exponent that I bring out front is that 3 on top. It's 3 log base 3 of a. When we expand division, it becomes subtraction, and then that exponent's going to come to the front. So 4 log base 3 of b. And that's as far as we can go with the expansion of this expression on the left-hand side. All right, just a couple more. If I do log base 25 of 625 radical x, I like this one. Okay. There are two properties happening here. First of all, we do have multiplication. We have the multiplication of 625 and radical x. The other thing I want you to think about is when you have square root of x, that's the same thing as x to some power. And what power am I raising x to if it's radical x? Hopefully from the last unit and earlier units of study, you remember that that's x to the 1/2 power. Perfect. So now that I have this written as a power form, we can expand it to log base 25 of 625 plus the 1/2 is going to come out front. So plus 1/2 log base 25 of x. And that's sort of simplified as much as we can go. I'll tell you that if you have numerical parts that are being multiplied or even part of a quotient there, you want to think about, can I evaluate that and make that a simpler number here? Because remember, this number is 25 to some power equals 625. Turns out that that's just 2. 25 squared is 625. So therefore, I can just replace that whole thing with a big old 2 plus 1/2 log base 25 of x. That's the kind of most simplified form of what we started with in number 3. Okay. One more example. Let's do log base a. It doesn't really matter what the base is, by the way. The properties still hold the same. Of x divided by yz. Okay. So for this one, when we expand, we have a product in the denominator. And that can get a little bit weird, but what I'll tell you is when we start the expansion, it's going to be log base a of x. And then as soon as I see division, I know we're going to have to subtract in our expansion. So what am I subtracting? Well, if there's multiple things in the denominator, it might be worth it to put them in a big set of parentheses when you expand them. Okay, or you can put brackets there like I have. It's kind of up to you. But I'm expanding a product. So I know product expands to addition. So it's going to be log base a of y plus log base a of z. Okay, so that's the completely expanded answer. Now, if you don't like the way those brackets look, certainly you could distribute the negative in. So this would be log base a of x minus log base a of y minus log base a of z. This is an equivalent answer that, of course, would be accepted. Notice how when you subtract 2 logs after log base a of x, what that would look like if I worked backwards, because that's what's coming next, by the way. Now we're going to take something that's already expanded out and we're going to work backwards and write it as a single logarithm. Okay, so subtracting twice really just means that a couple things are going in the denominator. Sometimes students kind of have a little bit of trouble visualizing that part of it, but we'll get some practice. All right, let's go in the other direction. So what is the other direction called? If we expand when we work this way, we're going to now work backwards, and we are going to condense some logs. And the part of condensing, the directions might also say write as a single log. So if the directions ever say write as a single log, it means there must be multiple logs that you want to condense so that the word log is only written once. All right, here's an example. So if I give you 3 log base 4 of x plus log base 4 of y, what would that look like if I condense it and write it as a single log? Going back to our properties, we're working kind of in the reverse direction now. We have what's on the right side. We want to work backwards and get to what's on the left side in a condensed format. Condensing is pretty important. Like I said, especially when solving equations, condensing is where it's at. All right, I'm going to write the word log base 4 once, and then I'm going to open up some parentheses. Okay, we're writing it as a single log. So when I do that, if you see a number out front, guess where that's going to go? Exactly, Angry Birds it back up to the exponent right there. Addition is going to condense to multiplication. So this is going to be log base 4 of x to the 3rd times y. And that's it. All right, here's another example. If I gave you 2 parentheses log a minus log b. Now keep in mind, if I don't write the base of the log in, this should have been something we talked about in day 1, that it's base 10. Okay, so if there's no base written in, we know we're working with log base 10. And therefore, if I want to condense this, we're going to get log of, well, I know that the inside part, subtraction, condenses to division. And what's that 2 going to do? It's going to go up as the exponent. And since the 2 belongs to this whole thing, the best way to write it, in my opinion, is put A divided by B and then square the whole quantity. Could you equivalently write A squared over B squared? Absolutely. Okay. But I think this is kind of the most concise way to write it. So I like that for number 2. All right, and then number 3, if we have 3 log base 2 of x plus 8 log base 2 of y minus 1/4 log base 2 of z, what would that condense to? Okay, well, let's write one big log base 2 here, and then think about all the properties that are happening. This has all 3, doesn't it? We have numbers out front that will come back up as exponents. We have addition, which will become multiplication. We have subtraction, which becomes division. So can you picture what this all looks like when condensed? Let's see. Log base 2 of x cubed. Addition becomes multiply, so multiply by y to the 8th. Subtraction means divide by z to the 1/4 power. Now, the only thing I'm going to hesitate a little bit with there, by the way, it's not z to the negative 1/4. The subtraction I took care of when I divided. Okay, but the only other thing I'm going to think about is z to the 1/4 is fine, but keep in mind that's the same thing as the 4th root of z. So more commonly when you condense, especially in multiple choice questions, you will see radical form used there as opposed to leaving something with a fractional exponent. Okay, so just kind of watch out for that and make sure that your skills of converting back and forth between fractions and radicals are good to go. All right, so we've done a little bit expanding, a little bit of condensing. And we're going to learn a new log function right now. Exciting, exciting things here. We already know what a common log is. A common log is log base 10. So when I say log x, like I mentioned a moment ago, that we're talking about log base 10 of x. Okay. But the new thing we're going to talk about is the natural log. And the natural log is super important to us because it represents the inverse of the natural exponent. If we remember what the natural exponent is, the natural exponent is something with base e. Remember PERT in the last unit? That's called the natural exponent. So what we have for the natural log is ln of x. Okay, ln, you've probably seen this button on your calculator for years and years and years and years. ln stands for natural log. It is equivalent to log base e of x. So if you think back to our last unit, if you were to graph the function f of x equals e to the x, remember e is about 2.718, right? The inverse of that function is the natural log of x. It has its own special designation because e to the x is so special as the natural exponent. So if you ever see ln of x used, we're talking about log base e of x. And with that being said, let's go ahead and take a look at some practice as it relates to the natural exponent. Okay, so let's do some quick evaluating practice. So first and foremost, if I said, what's the ln of e? The ln of e is 1. Because remember, this is the same thing as saying log base e of e. So if the power here is e to the first, then when the base of the log and the base of the exponential match, the answer is the exponent. Okay, so then I can pretty easily extend this to ln of e squared. ln of e squared is 2. Because log base e of e squared is 2. What about the ln of 1 over e to the 5th? Maybe we don't like that one as much, but when it's e to the 5th in the denominator, why don't we write this as e to the negative 5th? Okay, so now that I have this base e written with that exponent negative 5, the answer there is negative 5. How about the ln of 1? So if we're not sure about that, log base e of 1 is what we're looking for. E to some power has to equal 1. Can we find an exponent that makes that true, that e to some power equals 1? Answer is yes. It happens to be 0. In fact, log base anything of 1 is 0, right? It was log base 2, log base 7, log base a million of 1. Always going to be 0. All right, well, what about the natural log of 2? ln of 2. Turns out we need the calculator for this one, because we don't know e to some power. It's never going to really nicely give you that answer of 2. And if you double check it on the calculator, it's 0.693. I don't know. I better be right about that. Let's see. ln, by the way, is the button next to the 4. I use it so often that it's coming off of my calculator. But if you take a look, log's right above it, right? So the natural log of 2 is 0.693. Apparently that's an important enough value that I just have memorized it. Okay, 0.693 is what it is. Okay, so we know how to evaluate. Guess what? We can expand and condense with natural logs too, just like we can expand and condense with any log base. So if I said to expand the natural log of 2x cubed y over z to the 4th. Oh boy, lots of pieces there. Well, we know what to do with powers. We know what to do with multiplication. We know what to do with division. Just be careful that in the numerator, you're really multiplying those 3 things. Okay, the 2 is separate from the x cubed, which is separate from the y. So when I expand that, it's going to be the natural log of 2 plus, bring the 3 out front, 3 ln x plus ln y. Finally, minus, bring the 4 to the front, minus 4 ln of z. Okay. And I'm sure I've mentioned this before, putting that line through the middle of your z, I think really helps to differentiate if you have 2's that look like z's. You know, you wouldn't want to make a mistake sort of between your z's and your 2's there. All right, finally, what if I ask you to condense something like 1/2 ln a minus 5 ln b minus ln of c? Okay. So for this last example here, we did something earlier where we had the minus minus. Maybe you remember what that looks like when it was all condensed on the other side. What I think helps in this case is to actually take a negative from these two, because I don't want to do divided by divided by. It makes a complex fraction. But if I write it like this, where I take out this negative at the end, I can now see there's really only one division happening. It's dividing by some sort of product of these two. So if I were to rewrite this as a single logarithm with one natural log here, it would be the ln of, well, first of all, don't forget to Angry Birds the 1/2 here, ln of radical a, because a to the 1/2 is the same as radical a. And then I'm going to divide by the product of b to the 5th times c. What I don't like the look of is if you go back here, I don't really like the look of radical a over b to the 5th over c. That gets really messy looking. Don't stack all these fractions, because then you're not going to know, like, well, how does that actually simplify? All right, so don't do this. If it helps you to think of it, take out the negative from that group that's being subtracted, and then that becomes a product in the denominator, okay? I think that's going to just make life a little bit easier there. So we'll stop there for day 2 notes. There's some really good properties happening here. Now we know natural logs too. Boy, only 2 days in, we know a lot about logs already. All right, if you have any questions about these properties, plenty more practice to come next time I see you in class. Have a great day.